So first of all, so I have arranged in this way by a picture of Professor Kobayashi. So I cannot remember the exact time of taken when this photo has been taken, but just I say that I like this photo very much. So secondly, so before starting my mathematical talk, so I would like to say something about Professor Kobayashi and together with me, little. So so this means this I would like to thanks. So let me say something about Professor Kobayashi. Let me for this. So if I say in details, then it will take many times. So it will be another history. So just very briefly. So let me say the few words given below. So I have been with Professor Kobayashi since 1998 till date, and I have been attached also with Professor Sekiguchi since then. So as I said before, that it will be a long story if I want to say in details of these facts here, but so I do not do this now. But I hope to do this in some other occasion if I have this opportunity or chance of expressing my thanks or like this. Okay? So just few words I wanted to let you know that. So yes, so indeed it is very hard but much important job to make something, to make a thing possible from an almost impossible one. I have been used to doing it from a very early stage of my life. So on the way of such a journey of my life, I got Professor Kobayashi as a very cordial, supportive person. That support has become a great inspiration for me. As a result, my journey has been more smooth than before. Also, I wish for myself so that I can apply and implement all guidance, whatever I have been getting from him. Still I am getting support from him. I always pray for very good health for him. So, and my heartiest congratulations for Toshi. So you know, sir means sensei in Japanese word. This is the Japanese word. So I say happy birthday to you, my dear sensei. And here, so one name I am sure Oshima sensei is here. So another person was Oshima sensei. So I am sorry that I should put his name, but I say because he is here. So he was, so I cannot express, I have no adequate word to say. So from the very beginning, he was also my, so like father, in a word, I say that. And now my colleague has been my colleague, his son has been my colleague. So yesterday I called Oshima, then Oshima sensei was beside me. He responded. So in Japanese, so we say "Bikkurishimashita." So now I start my talk with the title page. So I should go back. This is my title page. Okay. Oh, okay. So this pointer I can use, no problem. So, First of all, so now I start my talk. So first of all, I would like to thank the organizing committee, Professor, who is our Professor Hideki Sekiguchi, Yoshiki Oshima, Takayuki Okuda, Yu Ichiro Tanaka, Masatoshi Kitagawa, Toshihisa Kubo. For in maybe these 6 persons are in the organizing committee, I think so. So please, I am sorry to say that, please excuse me if I do not indicate another name or like this. So these 6 persons is okay. So for inviting me to participate in this wonderful conference, I feel really honored to be invited in this conference. And I would like to talk about an interpretation of Kobayashi's theory on multiplicity-one representations. So I may be here. Representations in branching laws from the viewpoint of the orbit philosophy of Kirillov, Kostant, and Duflo and Vogan. I feel I would now let me say something again about Professor Kobayashi, that I like also to express my sincere gratitude to Professor Kobayashi, who has been inspiring me always by original ideas, continuous tireless guidance, and always by something new which are really immeasurable. So next, I have this. So here is the main object of my main objective of my presentation. I plan to explain some geometry of coadjoint orbits inspired by the theory of Professor Kobayashi on the restriction of unitary representations. The orbit philosophy suggests an intimate connection between coadjoint orbits of Lie algebras and irreducible representations. The left to right is considered as a geometric quantization of Hamiltonian manifold. On the other hand, important theorems in representation theory are sometimes discovered by different method and not by the orbit method. In that case, it may be worth searching the counterpart in the coadjoint geometry. In my talk, I discuss some coadjoint orbits corresponding to the theory of Kobayashi, such as visible actions, discrete decomposability, and uniformly bounded multiplicity-free theorems, and so on. Next, here is the outline of my presentation, of my talk. First, we recall Kobayashi's ABC program on the branching problems, namely the restriction of representations to subgroups. Second, we apply some Kobayashi general theorems to specific cases, such as the following this symmetric pair, such as the following symmetric pair of the indefinite orthogonal group OPQ. For instance, some multiplicity-one theorem for the restriction of small infinite dimensional representations. Finally, we discuss what the corresponding geometries of coadjoint orbits are. So next, in general, it is a very hard problem to study the restriction of infinite dimensional representations to non-compact subgroups. Professor Kobayashi proposed what he calls ABC program. The first stage A is to develop abstract theory of the restriction, which includes the study about spectrum and multiplicity in the general setting. Then stage A would single out special but nice settings in which we could expect a further detailed study in stage B, in such as finding an explicit branching law, or in stage C, such as the construction of symmetry breaking operators or holographic operators. We may think of an analog in the geometry of co-adjoint orbits for stages A and B in Kobayashi's program. Next. Professor Kobayashi himself made many pioneering works in stage A, namely abstract feature of the restriction in the general setting. It includes notably the theory of discrete decomposability of the restriction of representations in the non-compact setting. And Kobayashi discovered a criterion by an analytic method such as the wavefront set and by an algebraic method such as associated varieties. Another example of stage A is the multiplicity-one theorem, a systematic construction of multiplicity-one theorems from old to new, from finite dimensional to infinite dimensional by using visible actions on complex geometry, developing the idea of Gelfand, Farah, and Thomas. Yet another contribution of Professor Kobayashi to stage A is to initiate the study of finiteness of multiplicities, also the study of uniformly boundedness of multiplicities for both induction and restriction. The notion of real spherical space was formulated 30 years ago by Professor Kobayashi to describe a necessary and sufficient condition for the finiteness of the multiplicities. The main machineries for this problem by Professor Kobayashi and his collaborators Toshio Oshima, Tauchi or Tauchi and Kitagawa is differential equations such as hypervalued boundary maps and the theory of regular holonomic D modules. Next. Such a general theory in representation theory, such in representation suggests us a lot of interesting questions in the geometry of co-adjoint orbits, symbolically written as QR equals RQ, namely whether the quantization commutes with the reduction. Quantization at the conference in honor of the 50th birthday of Professor Kobayashi in France about 10 years ago, I gave a talk about QR equals RQ in certain non-compact setting. corresponding to the specific result of Kobayashi is as follows. This result, namely, any highest weight modules of scalar type decomposes multiplicity freely when we restrict it to any symmetric, deductive symmetric pair, or any, we can say, any symmetric pair. The subgroup is not necessarily compact, and the multiplicity for the continuous spectrum is also free for almost everywhere. Similar statement holds for another real form by replacing the multiplicity freeness with uniformly boundedness of multiplicity, like the second statement. Today, I plan to discuss about QR equals RQ in a different case, that the representation pi is not a highest weight module. So, next, our main object today will be the following symmetric pair: the indefinite orthogonal group OPQ, comma. So, when we write pair, then we write comma. The direct product of the indefinite orthogonal groups OP1 Q1 and times OP2 Q2. Roughly speaking, there are two types of Kobayashi's finite multiplicity or bounded multiplicity theorems. One is to treat for all irreducible representations of the group G, and the other is to treat only small infinite dimensional representations of the group G. For the former case, where we consider all irreducible representations, the uniform boundedness property gives the constraints on the pair of groups. For instance, the uniform boundedness property amounts to P1 plus Q1 equals 1 or P2 plus Q2 equals 1. On the other hand, the finite multiplicity condition gives a weaker constraint on the symmetric pair, and the necessary and sufficient condition is either the above condition holds, or at least one of P or Q is equal to 1. On the other, these are quite strong constraints because we consider all irreducible representations pi. On the other hand, if we consider only a small irreducible representation pi, all the parameters P1, Q1, P2, Q2 will be allowed, as we shall see in the next slide. Professor Kobayashi discovered, may I have some water, please? So, I resume now. Professor Kobayashi discovered and formulated also that if the infinite dimensional representations are small in some sense, then we could expect larger possibility for the bounded multiplicity theorems of the restriction. Here are some specific results of the general theory of Professor Kobayashi. The point of the first statement here, the first statement is here, is that the bounded multiplicity theorem holds for arbitrary reductive symmetric pairs if the representations have the smallest Gelfand-Kirillov dimension. In other words, if the associated variety of the representation phi of the group G is the minimal nilpotent orbit, we have a uniformly bounded theorem, multiplicity theorem for the restrictions of for arbitrary reductive symmetric pairs. Another important setting is that a representation phi has a non-zero distinguished vector for some non-compact subgroup H, which forces the representation phi to relatively small. In this situation, Professor Kobayashi has classified all the triples G, H, G prime such that the bounded multiplicity theorem holds for any representations pi with non-zero distinct vectors in the branching law to another subgroup G prime. We apply these results to the symmetric pair G, G prime equals, as I said, OPQ and the direct product group OP1 Q1 times OP2 Q2, and explain their counterpart in the geometry of co-adjoint orbits. I have no time. So, we recall orbit method in the theory of unitary representations due to Kirillov, Kostant, Duflo, and Vogan, among others. Loosely speaking, it gives a parametrization of the unitary dual. So, we mean by unitary dual the set of irreducible unitary representations of a Lie group by means of the co-adjoint representations of the dual of the Lie algebra therein. The orbit method works perfectly for simply connected nilpotent Lie groups, as Kirillov proved 60 years ago. This correspondence is functorial and relates to groups for induction and restriction. Such a functoriality also works perfectly for nilpotent Lie groups. However, the orbit method does not work perfectly when the groups are semisimple Lie groups. Nevertheless, we hope to find some nice geometrical results for co-adjoint orbits if there are nice theorems in unitary representations and vice versa, even for semisimple Lie groups. So, for instance, if we consider the restriction of a representation phi of a group G to a subgroup G prime, this is G prime, the functoriality or functionality, we can say also functionality of the orbit philosophy may be phrased as quantization commutes with reduction. We are interested in the non-compact setting. An important quantity of the representation theory side is the multiplicity, which counts how many times another irreducible representation tau of the subgroup G prime occur in the restriction of the representation phi. The orbit philosophy suggests us that this multiplicity will be computed by the data of co-adjoint orbits. Through the canonical this projection, this is the canonical projection from the dual of the Lie algebra to the dual of the Lie subalgebra. This is G asterisk, we say G German lowercase letter. This is G prime asterisk. This is for the Lie algebra, dual of the asterisk means dual. Everybody we know very well here. But further I want to say that this number, okay, this number is referred to as the Corwin-Greenleaf function. Concerning the multiplicity of restriction, the quantization commutes with reduction in the case of nilpotent groups. For holomorphic discrete series representations of semi-simple Lie groups, the quantization commutes with the reduction also in the non-compact setting. A number of mathematicians have contributed to this, including Professor Kobayashi, Oersted, Vagne over than 20 years ago, and more recently also by Faradan among others. Maybe Faradan is present here today also. So I met him yesterday. I don't know, however, today. The commutativity of quantization and reduction for holomorphic discrete series representations was the topic that I gave a lecture at the occasion of 50th birthday conference of Professor Kobayashi in Reims 10 years ago. In this talk, we consider such a problem more general irreducible representations such as minimal representations and Zuckerman's derived functor modules, trying to find the counterpart in the geometry of coadjoint orbits corresponding to Kobayashi's theorem in a specific setting, that is G equals the indefinite orthogonal group OPQ and G prime is the direct product group OP1 Q1 times OP2 Q2. We shall discuss coadjoint geometry through the canonical projection map. This projection map between the dual of the Lie algebras. This is the dual of the Lie algebras of the Lie groups G1, G2, and G1 times G2 equals G prime. G1 means, I think everybody understand in this audience. G1 means OP1 Q1, G2 means OP2 Q2. The first main theorem of my talk today is the coadjoint geometry corresponding to Kobayashi's uniformly bounded multiplicity. Uniformly bounded multiplicity theorem for the restriction of irreducible representations with the smallest Gelfand-Kirillov dimension. Kobayashi's theorem holds for arbitrary symmetric pairs, but we limit ourselves to the case G equals the indefinite orthogonal group OPQ. We denote by O min this O min the minimal nilpotent coadjoint orbit. Then there exists an open dense G prime invariant subset such that the intersection of this set with the full inverse of any coadjoint orbit of the subalgebra. O prime is the coadjoint orbit of the subalgebra G prime is a single orbit of the group G prime unless it is empty. That is, the Corwin-Greenleaf multiplicity function takes the value either 0 or 1. We can classify co-adjoint orbits O prime of the subgroup such that the asterisk is equality. So this means equal 1, but omit it here for the moment. In the case that P plus Q is even, then there exists a minimal representations of the group G equals OPQ, and the formula fits well into the explicit branching law obtained by Kobayashi and Oersted by using conformal geometry. This is the previous slide, that is, I think this is slide 10. Our theorem 1 may be considered as an analog in the geometry of co-adjoint orbits corresponding to Kobayashi's uniformly bounded multiplicities theorem for the smallest representations, namely the first statement of this fact, as we saw before. Next, we look at the second statement, which gives another uniformly bounded multiplicity theorem of Kobayashi. Here, pi is of H distinguished vector, namely pi is realized in a space of functions on the homogeneous manifold G mod H. I set up the notation for some irreducible unitary representation of the indefinite orthogonal group OPQ. Let XPQ be the generalized hyperboloid endowed with a pseudo-Riemannian metric of signature P minus 1Q. We consider the space of the square integrable eigenfunctions of the Laplacian. We recall results from Farah and Streicher's. This result. If we normalize the eigenvalue by the row shift, then the point spectrum of the Laplacian is precisely this set described by this set A plus PQ. Moreover, the group OPQ acts irreducibly on its L2 eigenspace, and we denote by pi plus lambda the resulting irreducible unitary representation. This is the family of irreducible unitary representations that we are going to discuss as branching problems. Next. Another uniformly bounded multiplicity theorem of Kobayashi for small representations is formulated by the property that irreducible representations pi have non-zero distinguished vectors, namely those representations that arise in the function space of homogeneous spaces. Based on his criterion for bounded multiplicity property, Kobayashi gave a complete classification of all triples of the groups for which these triples of the groups for which the uniformly bounded property holds. His list includes the following case where the subgroup G prime is the direct product group OP on Q1 times OP to Q2. We now take pi to be the discrete series representations pi plus lambda that Farah and Stizas obtained. So if I go back to Farah, this pi plus lambda. So then next, okay. And later generalized by Flenstedt, Jensen, and Oshima Matsuki. In this case, the general theory of Kobayashi implies that the multiplicity of the restriction is uniformly bounded. And more precisely, Kobayashi also found all discrete spectra for the restriction and proved that all the multiplicity is exactly 1. This is also what Ben Orsted explained in his talk here yesterday online on the Zoom platform. We now consider what are the counterparts in the geometry of co-adjoint orbits. For this, we need to do a different interpretation of Farah-Stiz's discrete series representations. So again, maybe Farah-Stiz, where is this? Okay. Then next, here I am now. Okay, maybe. Okay. For this, namely, so Farah Stiz discrete series representations. I went back to show this, to recall this. Namely, from the viewpoint of geometry quantization. For later purpose, I prepare the notation H plus, this H plus and H minus for two subgroups of G, of the group G equals the indefinite orthogonal group, I can say OPQ. Then we can think of discrete series representation for pi G mod H plus minus. As before, which we denote by pi plus and pi minus respectively. These are. Coincidentally, the same unitary representations arise as the geometric quantization of elliptic co-adjoint orbits as follows. First, we write, everybody we know very well this fact. So first we write the Cartan decomposition of the Lie algebra J equals K plus P. So German lowercase letter these are, and take H to be either H plus or H minus. This H is Lie algebra of H plus, the group H plus, and this H minus is the Lie algebra of this group H minus. Okay. We take a linear form lambda, linear form. So this should be linear form, should be an element of, is an element of the dual, everybody know, of G, of the Lie algebra G, that vanishes on the subspaces H and P, and consider the co-adjoint orbit O lambda, okay, O lambda that goes through this linear form. O lambda, this lambda vanishes on P, and a co-adjoint orbit of this property is called elliptic orbit. This is called the elliptic orbit. The general theory shows that any elliptic orbit carries a complex structure. Under an additional integrality condition on lambda, we can think of a Dolbezian cohomology of the equivariant line bundle with twist lambda, which gives the maximal globalization of the unitary representation of pi plus lambda or pi minus lambda. Alternatively, one can construct algebraically the underlying GK module by using Zuckerman's derived function modules, as I said before. In summary, we can reinterpret discrete series representations purely by means of co-adjoint orbits in connection with the branching laws of the unitary representation via the orbit method. We are now ready to state some results on the geometry of co-adjoint orbits. We retain the previous notation. In particular, O lambda is this O lambda is the elliptic coadjoint orbit going through lambda, which vanishes on H. This H. This is the Lie algebra of the Lie subgroup of H. Okay? If in addition lambda satisfies certain integrality condition, which precisely means that lambda belongs to the parameter set A plus PQ that we saw in the previous slide. So in slide 16 or 14, so I go back, so let me stop. Here is a lambda. I think this is the this, okay, this A plus PQ, this lambda. So I next, okay, I was here, yes, this integrality condition. Then one has the geometric quantization, which is unitarily equivalent to a discrete series representation for the orthogonal, indefinite orthogonal group OPQ over the indefinite orthogonal group OP minus 1Q by Farah and Streicher. So I think should I show the fact of Farah Streicher again? Maybe no need, or so later I will show. So where is Farah Streicher? Here in slide 16. Okay, this fact. Okay. In the theorem below, we do not need such an integrality condition. Now, our theorem 2 asserts that the following three conditions are equivalent. The first and second ones concerns the geometry of co-adjoint orbits. This first and second. That is, the canonical projection is a proper map when we restrict to the co-adjoint orbit that we consider. This means that the full inverse of compact sets are still compact. The third condition gives a necessary and sufficient conditions when this occur. In the next slide, we shall see that this condition corresponds precisely when the restriction is discretely decomposable. namely by the general theory of Professor Kobayashi on the discretely decomposable restriction. One has the following equivalence in our special setting. So, the discretely decomposability of the restriction of the unitary representations is equivalent to the properness of the canonical projection for co-adjoint orbits in this setting. If I go back to this is our theorem 2, and this is the fact, general theory of Professor Kobayashi. So again I go back, this is theorem 2 and this is the special fact of the general theory of Professor Kobayashi. This is a generalization of what we knew for holomorphic discrete series representation. We now look at a more precise formula for branching laws. The second fact presents here an explicit formula of discrete spectra of the restriction proved by Kobayashi. This fact. If all of P1, Q1, P2, Q2 are at least 2 and lambda is large enough, this formula shows that the discrete part is divided into 3 family of irreducible representations. 2 of them are infinite sums and the middle one is a finite sum. We also note that the branching law involves continuous spectrum too. Let us consider the counterpart of the coadjoint geometry. For this, we need to fix parameterization of coadjoint orbits. Let Eij be the matrix unit and lambda a non-negative real number. We introduce the following notations for some elliptic coadjoint orbits of the group G equals the indefinite orthogonal group OPQ. Here we have identified the Lie algebra with its dual Lie algebra G with its dual G asterisk by the Killing form. These elliptic orbits, coadjoint orbits, and these orbits are elliptic coadjoint orbits and have a distinguished property that they vanish on the subalgebra OP minus 1 Q or OP Q minus 1 respectively. Conversely, any elliptic coadjoint orbit having this property is expressed in this way for some lambda. Analog notation will be applied to subgroups such as OP on Q1 or OP to Q2. We recall our setting that G prime is the subgroup of the indefinite orthogonal group OPQ such that the pair G prime is a reductive symmetric pair. We are ready to describe the image of coadjoint orbits under the canonical projection. corresponding to the discrete series representation obtained by Farah and Strizas. So I should go back to the, I think it's okay. Time. So I go back. Farah and Strizas result maybe 16. Okay, this time. Okay. So I was in slide 22. Next. Okay. We consider a non-zero elliptic coadjoint orbit that vanishes on the Lie algebra OP minus 1 Q. Such a coadjoint orbit is expressed in our notations as O plus lambda G for positive lambda. Now we describe the image of such coadjoint orbits under the canonical projection. Let OG1 and OG2 be non-zero elliptic or coadjoint orbits of the subgroups G and G1 and G2 respectively. Then the direct product of them belongs to the image if and only if one of these conditions holds the following. One of these conditions is satisfied. Holds mean that is this is the necessary and sufficient condition. Moreover, the Corwin-Greenleaf function is exactly 1 in this case. This description fits well with the explicit branching law, as we saw before in the second fact of this slide, this fact. So, this is the end of my talk. Thank you very much for your patience. And again, at last I say happy birthday to you, my dear sensei.